The last time you heard my sweet voice, we were making graphs of vapor pressure versus temperature. And we had a graph that looked like this. It was like, whoop, and we found that it was really cool that when external pressure, P external equals P vapor, then boiling. That was really cool. So there's something interesting. I mean, I guess this represents some sort of a phase change. At this point right here, our fluid would go from a liquid to a gas or a gas to a liquid. Let's think about it. If we have a gas at this point right here, and we increase the pressure, maybe that's a little bit harder to consider. Let's start by taking a gas that's, maybe I should say a fluid that's right here. And I want to increase the temperature. Would you believe that I could go from this phase to this phase? If I increase the temperature, I'll be more likely to get a gas, right? I'll be more likely to get a higher energy for the particles that are in here. And then, this is a fluid down here. And then they'll be more likely to escape and not come back. There will be some coming back, sure, but there will be much more escaping. So that will be boiling, right? And then we'll get a much higher vapor pressure as a result. So but I'm not gonna allow the pressure to change. What I'm gonna say is if we take a gas and heat it, if we take a fluid and heat it, then we'll get a gas. So over here must be a liquid. So my next question is, what if we take a gas right here and we increase the pressure on it? Would you believe that we could also get from a gas to a liquid? I suppose we could. Yeah, what we're doing is we're putting more and more and more and more pressure on this gas, so it would like to condense. So that's another way to get from one phase to another. If we're going this way, we're going from gas to liquid. I guess we could go that way. We could go from liquid to gas if we cause the pressure to be less and less and less. This is the boiling that we talked about yesterday. You could decrease the pressure and then stuff will boil. You could also, you could increase the temperature to make stuff boil, or you could decrease pressure to make stuff boil. You could also decrease the temperature to make stuff condense, and you could increase the pressure to make stuff condense. Interesting. So this graph actually has a lot more stuff that we could talk about, and I'm going to make a fuller version of this graph, and it will be called a phase diagram. Here we go. This is zoomed way out on the previous diagram, and we'll try to call out where exactly it is that, that our old diagram existed. But I'm going to try to draw this stuff carefully. It goes like this, and then a typical substance would go like that, and then like this. And out here is called a critical point. So we got to label these suckers right here. This is a solid phase right there, and this is the gas phase over here, and this is the liquid phase over here. And the interesting thing is at this at this critical point right here, I'm going to label this. At the critical point, the distinction between a liquid and gas becomes negligible. So you can actually go smoothly between a liquid and a gas. This is really, really high pressure and really, really high temperature. So it's like this gooey slop, and you can't tell whether it's a liquid or a gas, and it's ridiculous to try to claim that you can. So let's go into this a little bit more. There's a critical point right here. This point is called the triple point because all three phases can exist simultaneously at the same temperature and pressure. It only exists at one temperature and pressure. So if you get a sphere of glass with some fluid in it and you get it to the right pressure, you'd need to get the right pressure, right? Then if you have it at the right temperature, then you could get all phases to exist. But if it's a little bit too cold, it'll be all solid. And if it's a little bit too hot, I guess it would be all gas. But if you get right there, solid gas, it'll be awesome. Absolutely awesome. So let's say that this is olive oil, and I don't know any of these numbers for olive oil, but characteristically, what I'm saying is if we go from solid olive oil to gaseous olive oil, we're going to have to be heating that stuff. And we'd have to be at extremely low pressure. You can't get from solid to gas if you're above this pressure right here. So if you're at extremely, extremely low pressures, this is like way, way pumped under a vacuum, and it's very, very hard to do for most substances, you can go from solid to gas. And that process is called sublimation. So we could call this the sublimation curve. Maybe that's how the band Sublime got its name. I don't know. Put it in the comments. Next. I guess you could go from gas to solid, and I don't even know if that thing has a name. It probably does, but it's like, gaseous solidification or something. There is one substance that comes to mind that at standard pressures, atmospheric pressure, it will go from a solid to a gas. And that is, you tell me. And then, let's see, we could also study this line right over here. We could go at a more healthy pressure. We could go from a liquid to a gas by, well, heating it. Excuse me. They tell me that this becomes carcinogenic when you actually boil olive oil. It makes these things that make you sick, so you probably shouldn't do that. Don't burn your olive oil. Use it for low temperature cooking. But if you get your temperature up too hot, then that sucker will boil. Believe me, it's happened to me also. And that's at the same pressure. But, you could, so what are we going to call this curve? You want to call this curve, I don't know, the boiling curve or something? Let's call it the vapor pressure curve, because we've already talked about vapor pressure. Vapor pressure curve. And there are names for all of these things in English. Yay, English. We're going from liquid to gas. We are boiling. And if we're going from gas to liquid, then we are condensing. And you could also say from liquid to gas is evaporating. That is becoming a vapor, tied in with the vapor pressure curve, etc. We could also, at standard pressure, we could go from a liquid to a solid, and we would do that by decreasing our temperature, and that's called freezing. So this, you could also call it fusing if it's not water. So this is a fusion curve. Oh shoot, I'm supposed to be in red. Fusion curve. There's a lot of very interesting stuff about this. And of course, if I'm going from a solid to a, do you want me to label all these things? No, I don't need to do that. If I'm going from a solid to a liquid, then that's called melting or liquefying if it's not water. We've got all these words for water, and we're usually thinking about water as our ideal fluid, but water is a good bit more complicated than this, so we have to start with olive oil. So there you are with olive oil, and if you have any questions, then we can address those if you ask me. But I want to draw a similar graph for water, and you will be stunned at what you find. Before we do it, I want you to notice that if I have a fixed temperature and I increase the pressure for olive oil, I increase the pressure, then it will eventually solidify, because the solid olive oil is more dense than the liquid olive oil. This is true for almost every fluid in the universe, but there is a beautiful exception, and that is the stuff out of which you are mostly made. So let's make another graph. We got temperature here. We got pressure here. This is water's phase diagram. And you're going to love it. Check it out. It goes like this, and then it goes like this, very similarly. And then you got your critical point out here. And that is a really high pressure when you can't tell the difference between gaseous water and liquid water. And, well, I mean, I guess that's really high pressure, really high temperature. It's like a extremely, extremely steamy sauna at really high pressures. Maybe an autoclave? I don't know. Maybe you need more than that. But I'm about to draw this line like that, and suddenly I stop and I remember, oh shoot, it's water. Check it out. Water goes like this. I'm exaggerating how much it goes like that, but the point is, if I have Watch this. This is my fusion curve over here. If I have some water, this is liquid, this is gas, this is solid. If I have liquid water and I decrease the pressure, then I can make it solidify. Similarly, if I have solid ice and I increase the pressure, I can make it melt. Whoa, ice melts if pressure increases. This is super funky. It means lots and lots of things. What we're really saying is that the density of ice is less than the density of water, especially water at 4 degrees Celsius. That stuff's some super dense stuff. It turns out that when water freezes, it expands, and this has a host of wonderful consequences. One of them is that when a lake freezes in the wintertime, lakes in the wintertime, that lake is going to freeze at the top because it's not very dense. So the top freezes and the bottom is still liquidy. And guess who gets to live through the winter? Your ancestors. What fun. And, oh, sorry, that's supposed to be a fish. Dang. There, I'll put a little fin up top. Sharks. And another consequence is that liquid water can go into the rocks because it rains sometimes, and little fissures in the rock get some water up in there, and those fissures, well, when it comes to be wintertime, those fissures are going to be forced open because when water gets colder, it solidifies, and that increases the volume that it takes up, and that's called frost heave, and that sucker will bust up stuff. In particular, if you're building a house, you want that house to have a strong foundation, right? You don't just set that house on the ground because it'll be shaking all around every time the ground freezes. You gotta dig down. Let me get some dirt here for you. Sorry, it's not going to be a happy color for dirt. You have to dig down here. It's called making a footing for your house. And in my area, you have to be 3 feet deep. You have to be 3 feet deep so that the ground, when it freezes, like this part of the ground here, this part of the ground's all gonna freeze in the winter, in the absolute worst times of the winter. Probably not inside your basement, so never mind. Don't say that that's going to freeze. But this ground over here will freeze also, and so you'll have your house shaking around unless you build it low enough. So you're gonna put some concrete down here so that that does not experience frost heave, and you will be just fine. Maybe you build some concrete blocks here, or pour yourself foundation wall. But the key is you have to dig deeply enough so that you don't experience frost heave. And it's also the reason that mountains crumble down to the sea, but there will still be you and me and all of that stuff. So water's really, really cool. And well, there's just one more thing that I want to say. I want to say, first of all, I have already pointed out to you that evaporation is endothermic. That means if stuff is evaporating from this fluid right here, what's leaving, the particles that are leaving are the very highest energy particles. And yeah, some are coming back in, right? But if there's a mass evaporation happening, or there's a breeze blowing and the wind that's coming in is dry, that's key to have a dry wind coming in, that makes you feel nice and cool if a dry wind blows by, because the wind takes with it those higher energy water particles that are on your skin. This is you're the beaker, and you're filled with some fluid on your surface, and the high energy particles go off with the wind, and none really come back. So if you are net evaporating, then you are losing heat energy. I guess consequently, and conversely, if you're drinking a soda pop, we don't say that where I'm from, sorry. If you're drinking a soda, and it says, I don't know, Mountain Dew on it, because that's awesome. If you're drinking a Mountain Dew and you get it out of the fridge, let me see if I can draw this thing, that'll be fun. You got this this opening here, and then this other thing that looks like that. Yeah, good, okay, that was pretty awful. All right, there's a Mountain Dew right here, and you got it out of the fridge. What are you gonna notice about that Mountain Dew? In just a moment, you're gonna have a whole bunch of this stuff going on here. If you got it out of the fridge. And if you sit it on the table in a sunny hot day, it doesn't even need to be sunny, we'll just have it be a hot, humid day in St. Louis. Yeah, St. Louis, you'll eventually get like a ring of water around it. Where'd that water come from? Is it leaking from inside the can? Shoot, no. You are condensing. And the problem is, condensation nearly ruins the experience of the Mountain Dew because condensation is exothermic. I guess that means that when water condenses on the Mountain Dew, it leaves heat energy at the Mountain Dew, and the Mountain Dew warms up dramatically. So you could actually avoid having your Mountain Dew warm up quite so fast if you put it inside a plastic bag. Put that sucker inside a Ziploc bag right there. Yeah, and then it will not get the condensation directly on it. You gotta space it out a little bit. Maybe you wanna wrap it up in mittens or something, or get one of those cozies. That's what I'm talking about. There, and then you can sit down and drink that Mountain Dew in nice, dry comfort because every bit of water is dumping an entirely enormous amount of heat into your Mountain Dew. We do not want to talk about how much heat that is because that's for tomorrow. But the last thing I want to say is this. Well, it's kind of two things, but they're very strongly related. What I want to say is that if this is I'm going to make a probability graph versus, speed again. Speed of the molecule. And you remember we had this graph and it went like, let me get you some nice color. What if it came out like this? It'd be like that, right? But also, that depends on temperature, and it depends on temperature in a fancy way. What if I told you that if it were a little bit colder, I'm going to make it blue because it signifies being a little bit colder, it would be a little taller and a little earlier in right here. But my point is this. This might be boiling. This might be 100 degrees Celsius. And this sucker here might be 30 degrees Celsius. So this is a little bit warmer than room temperature, maybe a warm day outside, and this is boiling. And you notice that both of them have a very similar distribution. So what if there's this point right here where every molecule with this much speed manages to make it away? I don't know where that point is exactly, how much speed is required from a molecule of water to break away from the intermolecular bonds. It's probably pretty high. This might be something like 1,000 meters per second or something. I don't know, just throwing that number out there. We could probably calculate it, but I'm not that interested. But my point is, both the water at 30 degrees and the water at 100 degrees have a significant number of molecules that are faster than that critical speed to break apart. So evaporation happens at all temperatures. And that brings us back to the idea of phase equilibrium. And we were saying some things about if the phase is, oh man, what were we saying? We're saying that if evaporation is happening, but there's the sufficient vapor pressure, then the same amount of condensation is happening. And if evaporation and condensation, let's see, going out and coming back in, are happening at the same rate, then you could also say that nothing is happening. But if you've got net evaporation, like if you got some sweaty guy playing the drums, that sucker is going to be cooling off because his highest energy molecules are leaving, and you know that average kinetic energy is 3/2 kT for monatomic ideal gas. And so maybe it's something like that. Maybe it's 5/2 kT or 7/2 kT or something for a fluid. But suffice it to say that if the average kinetic energy goes down, there is no choice but for the temperature to also go down. And that's why you sweat. The final thing I want to say is another probability versus speed graph. And this is going to make a ton of sense if we're going to refer to the same equation right here. I want to think about having two different types of gas in a box. And one of those gases is a heavy gas. Whee! Maybe it's oxygen or something. And so oxygen has a very small speed range, but if I have a tinier gas, well, let's see, if I have a tinier gas, I know that the temperature of the gas determines the average kinetic energy. And my argument is this: the temperature of the oxygen and the temperature of the hydrogen, if they're both in the same box, has to be what? Here are some cute little hydrogens, and here are some oxygens, but the oxygens are big, right? They're like, dang, 16. I guess if you get two of them together, their atomic mass is like 32 or something. Wow, something like that. And the hydrogen, well, I'm saying that these guys are hydrogen. Those guys are hydrogen, and these blue guys are oxygen. The hydrogen is atomic weight like 2 or something. So yeah, these hydrogens actually have to have the same average kinetic energy as those guys, and you know that average kinetic energy is 1/2 mv square, and we got to take that average afterwards. There's the average right there. So we're saying 1/2 mv square, and m is much, much bigger for the oxygen than it is for the hydrogen. So guess what's got to be bigger for the hydrogen? Yeah, the average speed of those suckers. And those guys have this enormously broad distribution of very high speeds. And if you want to make this visual for yourself, you can very easily see it simulated. I want you to go do yourself a web search for PHET gas properties. And if you haven't spent a lot of time on PHET yet, then you need to get the heck there, because it's got some awesome simulations. The simulation that you want right now is gas properties. Pump yourself in a little bit of a light species of gas, and sorry, that would be here, and a little bit of a heavy species of gas, and just look at which one's going faster. Goodbye. More likely to get a higher energy for the particles that are in here, and then, oh sorry, this is a fluid down here, and then they'll be more likely to escape and not come back. There will be some coming back, sure, but there will be much more escaping. So that will be boiling, right? And then we'll get a much higher vapor pressure as a result. So the, well, but I'm not going to allow the pressure to change. What I'm going to say is, maybe that's a little bit harder to consider. Let's start by taking a gas that's, maybe I should say a fluid that's right here. And I want to increase the temperature. Would you believe that I could go from this phase to this phase? If I increase the temperature, I'll be more likely to get a gas, right? If we take a gas and heat it, if we take a fluid and heat it, then we'll get a gas. So over here must be a liquid. So my next question is, what if we take a gas right here and we increase the pressure on it? Would you believe that we could also get from a gas to a liquid? I suppose we could. That was really cool. So there's something interesting. I mean, I guess this represents some sort of a phase change. At this point right here, our fluid would go from a liquid to a gas, or a gas to a liquid. Let's think about it. If we have a gas at this point right here, and we increase the pressure. The last time you heard my sweet voice, we were making graphs of vapor pressure versus temperature. And we had a graph that looked like this. It was like, whoop, and we found that, it was really cool that when external pressure, P external equals P vapor, then boiling.